All right, it's my pleasure today to introduce Johnathan Bush, and he'll be telling us about maps of Čech and Vietoris strips simplicial complexes into Euclidean spaces.
Yeah, thanks for the introduction, Henry, and thank you very much to the organizers for the opportunity to speak today. I'd like to talk about maps of simplicial complexes into Euclidean space. And about the first half of my talk will be concerned with maps of just an arbitrary simplicial complex into a space. And then toward the end of my talk, I'll get back to Čech and Vietoris strips complexes in particular. So let me start by considering the problem of finding a Euclidean realization of a simplicial complex. In other words, a continuous linear embedding from the geometric realization of a simplicial complex into a Euclidean space. This is sort of kind of the obligatory slide for applied topology. As an example, I'm starting with typically a finite metric space. And on top of that, I build some simplicial complex like the Čech or the Vietoris strips complex. And if I'm starting with a finite metric space, the resulting simplicial complexes are finite and they're locally finite. And it's always, in that case, very easy to find a Euclidean realization. In this example, both the Čech and the Vietoris strips complexes that I've drawn here at this scale contain a 3 simplex. But I could get away with embedding this in R3, of course. Most of it could be in the plane, and then maybe, say, this vertex I could lift up into a 3rd dimension. So in practice, it's very easy to find these Euclidean embeddings or realizations for these sorts of complexes. But I'd like to consider starting not necessarily from a finite metric space, but starting from something that's maybe a manifold, for example. And the problem of finding kind of an analogous Euclidean realization or sort of an approximation to an Euclidean realization in the case that, say, the simplicial complex contains simplices of arbitrarily high dimension. So throughout, I'm going to assume that all of my simplicial complexes are connected and non-empty. And this is kind of a very minor point, but I'm going to make this assumption just so that some of the theorems, some of the statements that I make later, I can avoid some extra hypotheses. And this is also not really a big deal to assume that the complex is connected because I'll be considering this Euclidean realization. And if the complex is not connected, then just sort of do this component-wise, for example. Okay, so just kind of as a reminder, the geometric realization of a simplicial complex is a topological space that comes from the combinatorial information of the simplicial complex. So to a complex K, I'll define this set, which is bars around K. This is a set of formal finite convex combinations of vertices in K, such that all of the vertices in this combination make up a simplex of K. And by convex combination, I just mean I have a collection of non-negative real numbers whose sum to 1 as sort of weights on the vertices. To this set, we get a topological space by equipping this with, say, the weak topology, which is also called the coherent topology. And the idea is to basically for each individual simplex, construct some actual, like a Euclidean realization of that simplex, and then to glue all of these things together according to how their faces intersect. I'll call this, so this is called the geometric realization of K. And I'm going to use this notation to denote this space, which is maybe not standard, but I'll also consider later in my talk the same set with a different topology. So I'll use this, this notation to denote the geometric realization, whereas typically you might see just this notation sort of identified with the geometric realization.
John, really quick, we had a request. If you could move your black mouse cursor to the side.
Oh,
so
yeah,
it's not,
sorry.
Yeah, no,
Sorry. Yeah.
thanks so
I
much.
didn't realize it came through. Yeah. Yeah. Okay, so what then is a Euclidean realization? This is specifically a map from the geometric realization to a Euclidean space. And it's a linear map. So by linear, I just mean that the map needs to respect the convex combinations. So if I start with some point in that set, bars around K, in the geometric realization, this is some convex combination of vertices. The image of that combination is the same convex combination now applied to F of the vertices. So basically just extend this map linearly across these formal sums. We'll say that a simplicial complex K has a Euclidean realization in RD with respect to the weak topology if there's a continuous linear embedding from the geometric realization into RD. And then a very well-known theorem says that if a simplicial complex K is locally finite and it's of finite dimension D, then K has a Euclidean realization in R 2D plus 1. And again, this is with respect to the weak topology. A simplicial complex K is locally finite if every vertex is contained in a finite number of simplices. And this assumption is necessary for the realization to be compatible with the topology on the geometric realization. In other words, such a continuous linear map exists only if I make this additional assumption that the complex we start with is locally finite. And this is sort of a point set topology sort of proof that goes into this fact. And the reason that I'm kind of emphasizing with respect to the weak topology is, again, I'll consider a different topology on the same set, and we'll have kind of an analogous theorem in that case. All right, so before I define this alternative topology, let me sort of motivate it first by just pointing out that the geometric realization, when restricted to the vertex set, this has the discrete topology. And in applied topology, our vertex set is a metric space. And in practice, of course, this metric space is finite, in which case this isn't a problem. But say theoretically, I might want to consider what happens if I instead build this complex on not just a discrete metric space. So something like maybe the real line is my vertex set, or the circle or a sphere, or some sort of interesting space. Maybe that's my input to the Vietoris-Rips complex, and that's my vertex set. In that case, the geometric realization, because the vertex set always has a discrete topology, just sort of completely disregards or just loses all of that metric information. My vertices now, say take a simplicial complex whose vertex set is the real line, then say the Vietoris-Rips complex defined on the real line just has as its vertex set just an uncountable discrete set. We just lose the metric. And this sort of motivates the idea of the metric thickening of K, which is if I start with a complex whose vertex set is a metric space, I'll use the same underlying set as the geometric realization, but instead we'll equip this with the one Wasserstein metric or the n Wasserstein metric. And it turns out that the resulting space, so the metric induces this simplicial metric thickening topology on K. And it turns out that this space preserves the underlying metric space when restricted to the vertex set. In fact, the vertex set isometrically embeds into the metric thickening. So we do retain all of the metric information about the vertex set. Here's some facts about metric thickenings, some of the properties that they enjoy. They were introduced in 2018 by Michael Adamczyk, Henry Adams, and Florian Frick. And some examples you could consider are, say, the Vietoris-Rips or the Czech metric thickenings. They satisfy a metric Hausmann reconstruction theorem, which says that if you start with the vertex set, which is, say, like a Riemannian manifold with some assumptions, then at sufficiently small scales, the Vietoris-Rips thickening is homotopy equivalent to the manifold itself. And simplicial complexes, Vietoris-Rips complexes also satisfy this sort of property. And this says that so basically at small scales, as long as my vertex set is the manifold, then we do actually just recover the manifold itself. Recently and importantly, Adams, Memoli, Moy, and Wang recently established, among other things, and they do this in much more generality as well, but they established persistence stability for Vietoris-Rips and Čech metric thickening filtrations for any totally bounded metric space X. And this implies in particular that these filtrations yield the same persistence diagrams. And I say that this is kind of important because that means that in practice, one can choose to use basically the metric thickening version or just the simplicial complex, the geometric realization topology, depending on the situation. And I would point you to this reference for some good exposition about why one might use one over the other in particular situations. So,
and John, just to clarify, by same persistence diagrams, you mean the Vietoris-Rips metric thickening has the same persistence as the Vietoris-Rips simplicial complex.
Yes.
And Čech metric thickening, same as the Čech simplicial complex. Yeah, as you said.
Yeah. Thanks for clarifying, Henry. I see that I should have written that out. Yep. Yes. Okay. So let's consider this Euclidean realization again, this time in the context of finding this continuous linear embedding, but now with respect to the metric thickening topology. Completely analogously, we'll say that simplicial complex K has a Euclidean realization in RD with respect to that topology if there's this continuous linear embedding. And it turns out that it's already known that if we start with a metric space X, build this metric thickening on top of it, if I have a continuous and bounded map from the metric space to Euclidean space, then the linear extension to the entire metric thickening is also continuous and bounded. And this means that in order to find continuous linear embeddings of metric thickenings, I'm really looking for continuous maps from the underlying metric space to Euclidean space, such that when I do this linear extension, this is an embedding. In other words, the geometric simplices in Euclidean space intersect only along their common faces. And it turns out that there's a convenient map to use in a lot of situations to find such an embedding. It's called the moment curve map. And I'll define that on my next slide. But before I define it, I just wanted to also kind of have as a reminder what it means for points in Euclidean space to be in general position. In RD, points are in general position if no two of them coincide, if no three of them lie on a line, if no four of them lie on a plane, etc. And I should say that we can have arbitrarily many points in general position in a Euclidean space, but a set of at most d+1 points in RD in general position is said to be affinely independent. So I can have at most d+1 affinely independent points in RD. These 3 points are not affinely independent, of course, and these green points are. Okay, so the moment curve map then is something which makes it very easy to find a lot of points in general position. And this is not, I should say, not easy, but it's necessarily, I mean, it's easy to find points in general position. Of course, you just throw the points down randomly. But this is sort of a systematic way of picking out points in general position. And it's also a continuous map from the real line to Euclidean space. And it's defined by taking a number t to the vector t, t squared, t cubed, etc., up through t to the k. I plotted here gamma 3 for t between 0 and 1. And the property of the moment curve, sort of its defining characteristic, is that every set of at most k+1 distinct points on the moment curve is affinely independent. In other words, the image of the moment curve map is a set of points in general position. And the proof is fairly straightforward. I'll use the fact that a set of points in Euclidean space are affinely independent if I take those vectors and append ones to them, and in that Euclidean space of one dimension higher, if that set of vectors is linearly independent, then my original set is affinely independent. And this is an if and only if. So I'll take, say, k plus 1 distinct points, real numbers. Here are the images along the moment curve, append ones to them. And this matrix is a very well-known matrix called a Vandermonde matrix. And its determinant is known to be a product of the differences of the inputs, the TIs. In other words, if I start with distinct T1 through Tk plus 1, then this product will be non-zero. So the points are affinely independent. Okay, so then the analogous theorem for Euclidean realization of a metric thickening says that a d-dimensional simplicial complex K has a Euclidean realization in R 2D plus 1. Now, with respect to that metric thickening topology, if the underlying metric space X, which is the vertex set of K, admits a continuous bounded injection into the real numbers. And this is the proof sketch. So we'll consider this map F, which is this injection to the real line followed by the moment curve map. This is a continuous and bounded map from the metric space X to R 2D plus 1. So by that previous lemma that I wrote down, the linear extension to the metric thickening is also continuous. Furthermore, F is an injection, and I'm using that property of the moment curve map, so that the image is a set of points in general position. Now K is d-dimensional, which means that every simplex has at most d plus 1 vertices. So if I consider two different simplices, together they have at most 2d plus 2 vertices. And this is a set of points in general position along the moment curve in R 2d plus 1, which means that those points are affinely independent. And a property of affinely independent sets is that every point in the convex hull of that set has a unique representation in terms of its barycentric coordinates. It has a unique collection of lambda i's in that convex combination, which means that if I have two of these vertex sets, if I have a point that's contained in the convex hull of both of them, then it's necessarily contained in the convex hull of the intersection of the vertex sets. In other words, the intersection of any two of these geometric simplices in R 2D plus 1 is empty, or it's along a common face of the two simplices. So this really is an embedding. And this is my continuous linear embedding from the metric thickening into R 2D plus 1. And you'll notice that I actually don't need to make the assumption that the underlying metric space, or that the underlying simplicial complex is locally finite. Okay. That observation about the moment curve map motivates the consideration of simplex-preserving maps.
And John, let me ask you a question in the chat. So is there an easy example where the underlying metric space fails to admit such a continuous bounded injection to the real line?
Underlying metric space fails to admit a continuous bounded injection. If the metric space is the circle, for example, yeah, no continuous injection from the circle to the real line. Yeah, that'd be the Borsig-Ulam theorem for the circle. Yeah, that's a good question.
And this type of embedding using the moment curve, I mean, this would also work very well for simplicial complexes with the geometric realization topology.
That's right.
In many cases, well, yeah. But you're proving here that they also work with the metric thickening topology, which is
yes, and I should have said that explicitly, which is that this proof that I've written down here is essentially exactly the same proof that you could use for the geometric realization. There's just that point set topology thing you need to consider to ensure that the map is continuous.
Yeah, definitely. Thanks.
Yeah. Yeah, I can't see the chats, but I see that there's, oh, I see. Okay. All right. yeah, so this observation about the moment curve map kind of motivates the following definition, which says that for a space X and a continuous injection from X to say Rk, we'll say that F is simplex preserving if for any set S of cardinality at most k plus 1, if those are distinct points, then the image is affinely independent. So equivalently, a continuous injection F is simplex preserving if the image is a set of points in general position. For example, the moment curve map then is kind of our example of a simplex preserving map from the real line to any dimensional Euclidean space. So my question then is, do these sorts of maps exist for other domains X? Does there exist a simplex preserving map, say, from the plane to a higher dimensional Euclidean space, or from a sphere? And currently I have one result, which is about maps from the circle. And so we'll consider specifically maps from the circle to Rk. And for example, if k is equal to 2, then just the standard inclusion of the circle into the plane is simplex preserving, because the image of any set of 3 distinct points is affinely independent. Yeah, of course, no 3 distinct points on a circle belong to a line. And then this, I should point out that this doesn't work, for example, for S1 to R3. I can't just map into the plane and then include the plane into R3, because now I'm looking for a map such that any distinct 4 points are affinely independent. And it turns out the theorem then is that there exists a simplex preserving map from the circle to Rk if and only if k is even. So this is kind of this was kind of surprising to me that the existence of these maps, at least for the circle, kind of depends on the parity of the codomain. So I'll give a proof sketch. And one direction is fairly straightforward to find these simplex preserving maps. It turns out that there are these trigonometric moment curves. And so this is a map from the circle to R2k, defined by taking t to the vector, which is cosine t, sine 2t, sine 2t, etc., up through cosine kt, sine kt. If k is equal to 1, this is a map from the circle into the plane. So this is just t goes to cosine t, sine t. That's just that standard inclusion. These occur in even dimensions, so I can't draw the next one, which is in R4, but I have drawn here just the first 3 coordinates, cosine t, sine t, cosine 2t. You can get kind of an idea of how this curve looks when k is equal to 2. In the first 2 coordinates, I just sort of go around the circle. And in the third coordinate, I have cosine 2t. So I go up and down. And then in the fourth coordinate, we sort of do sine 2t. So it's also sort of doing that kind of thing. And that's the trigonometric moment curve. And it turns out that completely analogously to the standard moment curve, this satisfies the property that the points along this curve are in general position. So one can check that, again, append these vectors with 1s, take this determinant. One can check that the determinant works out to be a product of sine terms, where the arguments of sine are these differences of the ti divided by 2. So that if I start with distinct t1 through t2k plus 1, then all of these terms will be non-zero. Okay, so that's the existence. And now for the other direction, let's assume for a contradiction that there's a continuous injection from the circle to an odd dimensional Euclidean space. For the rest of this, I'm just going to consider k is equal to 2, just for the purpose of visualization. So let's assume we have a continuous injection from the circle to R3. It turns out that this map induces a continuous map, say capital F, from a simplicial 3 sphere to R3. And there's a recent result, and I'll describe on the next slide what this reference is, but there's a recent result which says that then disjoint faces of that simplicial sphere must intersect in the image of capital F. And it turns out that in general, this is enough to imply that the image of little f contains a set of 2k points that's not affinely independent. So the map F could not be simplex preserving. And in the case k equals 2, this simplicial 3-sphere, I can actually kind of describe exactly what it looks like. And if I get to my later slide, because I see that I'm a little bit behind schedule, but if I get to my later slide, I'll describe where this sphere is coming from. But the simplicial 3-sphere has as its vertex set the image. Sorry, I should say it has okay. Its vertex set is this curve in R4, and its edges consist of all line segments connecting any 2 points along that curve. So I have all of these line segments, and those are all of the edges making up the simplicial 3-sphere. And it actually doesn't have any higher dimensional faces. So this 3-sphere is just made up of vertices and edges. And because I have these things intersecting in R3, I should also say that now under this map to R3, the vertex set is exactly the image of little f. And I assumed that little f was an injection. So I know that I have these edges intersecting. They're not intersecting at vertices, they're intersecting in their interiors. And that gives me 4 distinct points which belong to a plane. So that proves that this map, little f, is not affinely independent. It has at least 4 points that belong to a plane.
And John, don't worry too much about the time. We'll keep interrupting you and slowing you down, but that's all right.
Yeah, that sounds good. Yeah. Okay, so what is this reference here, 6, corollary 1.4? It's this recent paper. I think this is currently just on arXiv, but it's called Tijverberg's theorem for cell complexes. In fact, Dr. Kishimoto gave a great talk about this paper through AATRN in August, I believe. And in this paper, the authors generalized the topological Tijverberg theorem now to a continuous map from a CW complex into a Euclidean space. And the topological Tijverberg theorem says something about a continuous map from a simplex to a Euclidean space necessarily has, with some assumptions, necessarily has disjoint faces intersecting. And they've now extended this theorem to more general CW complexes. And among their results is this statement about a simplicial 2k-1 sphere to R 2k-1 has disjoint intersecting faces. Okay, so now I can finally get to Čech and Vietoris Rips complexes and thickenings. And before I talk about a specific example, this is the trigonometric moment curve that we've seen and that I've used in the previous theorem. There's a centrally symmetric version of this map. By centrally symmetric, I mean that it respects the antipodal action on the circle and on Euclidean space. In other words, if I plug in a point on the circle, its antipodal point maps to the opposite vector. So this is defined by taking not just all multiples of t, but only the odd multiples of t, up through 2k-1. And it turns out that the trigonometric moment curve and the centrally symmetric trigonometric moment curve are in some sense approximations to simplex preserving maps for Čech and Vietoris Rips complexes when the vertex set is the circle. In particular, if the vertex set is the circle, then Čech and Vietoris Rips complexes at scale greater than 0 have simplices of arbitrarily high dimension. So of course I can't find a Euclidean realization. Any map to Euclidean space is going to collapse most of the simplices. But I'll try to describe exactly what I mean by these maps being sort of approximations to these simplicial complexes. And for that, I'm going to consider Čech complexes. And throughout, I'm taking the metric thickening topology just so that I don't have to worry so much about certain maps being continuous. But a lot of what I'll say here also just applies for just the standard geometric realization. Let's consider the example where R is equal to pi. With my definition of the Čech complex then, we have a simplex if and only if it's a finite set of points on the circle that is contained in a closed semicircle. We can consider the continuous linear extension now from the Čech metric thickening to R4, where M4 is that trigonometric moment curve. This is a map from the circle to R4, but I can just consider this linear extension, which is continuous by that previous lemma, where I take a convex combination of points to the same convex combination now of the images of the TIs. And then kind of as an aside, just as a reminder, if we restrict it to the 4 skeleton, then M4 is a simplex-preserving map. And that's because every set of 5 distinct points in the image of this map maps to an affinely independent set. Okay, and then additionally, I'll have you observe that the image of this map applied to the Čech metric thickening is a subset of the convex hull of the image of the map applied to the circle. This is take the curve in R4, take its convex hull. This is take this curve in R4 and take the convex hull only of points that belong to closed semicircles. And it turns out in a few slides, I'll describe actually, this is a proper subset. Let's consider the structure of this convex hull before I get to, let me say, let's just consider the facial structure of this convex hull. Again, I've drawn just the first 3 coordinates of the map M4, and I've drawn its convex hull over here. So really, the image of the actual map in R4 is a 4-ball, and its boundary is a simplicial 3-sphere. And this is exactly the simplicial 3-sphere I was describing earlier. So its vertices are all points along this curve. Its edges are all line segments connecting pairs of vertices, and it doesn't have any higher dimensional faces. This is, like I said, kind of an approximation, but you can see that the faces of this convex hull are the points along the curve. And also there are a lot of these edges, which are forming faces as well. There's a supporting hyperplane, which intersects only along one of these edges. This doesn't contain all of the faces, of course. I can't just take any 2 pairs of points along this curve, but in R4 I can. Okay, and then it turns out that a result due to Gilbert and Smith implies that the image of this map, when we restrict to the Čech complex or thickening at this scale, doesn't contain the origin. So this really is a hollow, it's a 4-ball that's been hollowed out. And in fact, one can show that the boundary of that thing, which is this 3-sphere, is a retract of the Čech metric thickening at that scale, so that the 3-dimensional homology, cohomology, and homotopy groups of this space are non-trivial. And this collection of pictures I've drawn here is just supposed to indicate kind of the infinite dimensional complex, all of these simplices of arbitrarily high dimension mapped into a Euclidean space, which collapses a lot of them. And this is this hollowed out ball, and its boundary is this 3-sphere. And this is enough to imply some results about homology and cohomology and homotopy groups. It turns out that this also works at all scales by considering this linear extension now not just along the map M4, but say M6 or M8. As I increase the scale of the Čech complex, we need to map to higher and higher dimensional Euclidean spaces in order for the image to miss the origin. And that basically we can get then at all scales, we have that these things are non-trivial in dimensions, say 3, 5, 7, etc. And an analogous idea also works for Vietoris rips complexes or thickenings, where in that case, we consider instead the centrally symmetric version of the trigonometric moment curve. Okay, so this is my final slide, and I decided to not get into detail about doing this for the Vietoris-Rips complexes, but it's kind of an analogous idea, which is to extend the Vietoris-Rips, extend the symmetric moment curve now, not just from the circle, but to the entire Rips complex, and do this linearly. This map is not quite simplex preserving, unlike the ordinary moment curve, but these maps have a lot of nice properties. For example, the simplices that make up, so the boundary of the image, the convex hull of the image is, again, it's a simplicial sphere. And that boundary is made up of simplices that have bounded diameter, for example. So if I consider the pre-image of those vertices, they have bounded diameter in the circle. So that's one nice property. And another property is that it takes, for example, if k is equal to 2, this is a map from the circle to R4. And it has this property that if I take 5 equally spaced points along the circle, if I take this 4 simplex, then under this map into R4, we actually have a regular 4 simplex. So the distance between any pair of points, distinct points, is equal. So it takes this kind of approximation to a regular 4 simplex to an actual geometric 4 simplex in R4. And it does this for, say, if k is equal to 3, then I take 7 equally spaced points, etc. Okay, so I'll end with some questions. I've already asked, do there exist simplex preserving maps, say from spheres or higher Euclidean spaces? I have not a lot of intuition about if such maps exist, but I would conjecture that for maps from the sphere to Euclidean space, S2, I would conjecture that the statement about precisely which dimensions admit a simplex preserving map would be much more complicated than the case for the circle. So I think that it would be something that's not just, say, the parity of the codomain. I think it would be something which is, yeah, I guess I won't make too much of a conjecture, but I just have a feeling that it will be much more complicated. And then additionally, the faces of the convex hull of the trigonometric moment curve are known. That was, for example, when I was describing that simplicial 3 sphere, there's an analogous description for all of these simplicial spheres in all of these even dimensions. But a precise description of the faces of the convex hull of the symmetric moment curve, this description is currently unknown if k is greater than 2. And there are some partial results, like I was indicating here. Certain things are known, but it's not known exactly what the faces are. And then finally, just kind of a general question, which is that it would be nice to understand better relationships between, say, the Čech and Vietoris-Rips geometric realizations and metric thickenings. And specifically, one conjecture is that for certain spaces X, these things are actually, say, homotopy equivalent if we take, say, the less than convention rather than the less than or equal to convention. So yeah, very general question. But I think that's all that I want to say. So thank you very much for your attention. And here's my references.
So before we get to questions, why don't we briefly unmute ourselves and applaud for Johnathan. All right, questions for John?
I have one.
So
okay. Hi, John. Can you see page 24?
Yes.
Okay. So you said the boundary of that convex hull is homotopy equivalent to S3, and it is a retract of the metric thickening of S1. So is the retract or deformation retract?
I guess it's a, I think it's a retract. Yeah, I don't know.
Okay.
Conjecture deformation retract, right?
Yeah, exactly. Yeah, that's
okay.
right. Yeah.
Okay. Thanks. Yeah.
Yeah, that's right. We would conjecture that it's
Hmm.
that it is actually the 3-sphere.
So the scale parameter pi here, John, is saying that in this Čech complex, you're taking the nerve of all arcs that go halfway around the circle. Is that right?
I'm taking, yeah, so I guess in my definition, I'm considering balls of radius pi over 2.
Right, right.
Yeah. Yeah, pi over 2.
I just have a comment related to Yi's questions in the chat. So John, you remarked how if you take all edges on the circle, then the union of these edges with the right topology is a 3-sphere, right? And that's what you use to prove that there are no simplicial maps from the circle into odd dimensional space, if I understood that correctly, right? So let me just say a generalization of that result. So if you take all edges on the circle, you get a 3-sphere. What's the right generalization of that? So if you take all simplices of dimension,
yeah, all 2 is that? Yeah, I think if you take all vertices, edges, and 2 simplices, you get the 5-sphere.
Right, and then if you take all vertices, edges, 2 simplices, 3 simplices, you get the 7-sphere. Yeah. I'll try to write it in the chat, the precise comment. More questions? So John, I was wondering if you could say a little bit more about this result by, was it Kishimoto that you were using?
Yes.
So what is the result that you're applying?
So I'm applying specifically one result in this paper, which says that a continuous map from a simplicial, say n sphere to Rn necessarily has disjoint faces that collide in the image of the map. Yeah, and this doesn't depend on taking like an odd dimensional space. And I should have made that more explicit, that their result is just for any simplicial n sphere to Rn.
Any further questions? Well, thanks so much, everybody. And I think we have a month off until our next talk due to Thanksgiving holiday in the US. But thanks again, John, and hope to see you all again soon.
Yeah, thanks for the opportunity to speak.
Thanks, John.